saving time and money. After completing the seminar today, you may be interested in additional training from ISA on safety, security, wireless, and more. Please be sure to visit www.isa.org/training for more information or to register.
We're dealing with a review of the materials for the Controlled Systems Professional Engineer examination. And we will have one more session following this. This is the 5th. Today we will be focusing on primarily final control elements, which is the 3rd domain in the specification for the exam, and it represents about 20% of that test as far as the contents are concerned. We want to talk a lot about control valves today and control valve sizing, and also a little bit about relief valves. There'll be some other areas that are dealt with on the exam, but due to time constraints, we will focus on this, which will be the main part of that content. Again, I'd like to commend you for your initiative in taking steps to further your professional development, to check into and to take part and be successful in obtaining your PE license, which I think is a very, very important step for you. And I commend you for that, and I hope that we'll be able to provide you a little assistance and help you in your studying and in your preparation for the PE exam. We had some people last session that contacted me that were traveling. We had some that were out of town and even out of the country, and certainly I hope you're able to take part this week, and I will give you some information later on about how to obtain some more sample problems that we'll be talking about in the course of today's presentation. If we go back a little bit and look at what we call a typical control loop, we've discussed what the process is and how that's part of the equipment, the pumps, the tanks, vessels, or whatever that make up the changing of conditions of some inputs that gives us some outputs with certain type of characteristics and certain elements and certain variables that we're interested in, different process variables that we may want to know more about as far as the process is concerned. These may be levels or pressure, temperature, or whatever type of variable that we're interested as far as the control is concerned. And then in some of our other sessions, we discuss sensors and transmitters and how we get that variable value into a standard signal, if you will, be it 4 to 20 milliamps, 3 to 15 PSIG, digital, or whatever type of signal that we might have that we apply to what we call a controller. And the controller may be part of a programmable system, a PLC or a DCS, or it can be a dedicated pneumatic, electronic type controller. But in any event, that intelligence is applied, given to us by our transmitter, and then the desired value of that control variable is set as a set point, either remotely or either locally, a cascade loop, where we talked about different types of loops and how we compare the measurement to the set point. And then depending upon the situation of the error, that is the difference between the measurement and the set point, and then we have our different control modes that we talked about. We generate the most important thing is a corrective signal that is generated and applied to some final control element, be it a control valve or a regulator, speed control on a conveyor, or whatever this might be. It is the final control element that does manipulate some input variable, input quantity. It might be cooling water, it might be steam, it might be hot water, it might be another chemical, but that is added to the process to mediate any disturbances that we may have that's caused our controlled variable, which is our process variable and our measure variable, to leave its desired state as determined by the set point. So today we're going to be talking about the final control element, a very important part of the loop. And many times it is a control valve. It might be other devices, but we're going to focus a lot on control valves because From past history, there will be problems dealing with control valves, the installation of control valves, the use of control valves, the application of control valves. So we'll focus quite a bit of that today, although there are other types of final control elements. Today, looking at control valve types, we want to talk a little bit about what is a control valve, what's some of the terminology, when do you use certain types of valves, and what are the characteristics of these body types, and what are the various components. These could all formulate opportunities for questions, so we need to actually understand and get a good foundational setup for what is a control valve. First, let's talk about just a typical control valve. If there was such a thing, we're going to call this particular schematic here a typical control valve. This happens to be a cutaway of what actually is a globe type control valve, but some of the terminologies will all be very, very similar. For instance, all the valves will have a valve body. This is the part that's actually installed in the line. It's a very, very important part called the body. That body may be flanged or screwed. It may be large. It may be small. It could be 1/10 of an inch. It may be 42 inches. But you do have the valve body, which takes certain forms that we'll talk about a little bit later on. But no matter the type of valve, you do have the valve body. And again, you may have flange connections. It may be screwed, butt weld, and the material of the body may be cast iron, carbon steel, stainless steel. It'll be some material that's compatible with the flow that's going through the line and with the piping specification. Then we have a very important part of the valve that's called the trim of the valve. And the trim is actually composed of any type of operating plug and the seating surface. In other words, the trim is the inner part of the valve and is very, very important. So you'll see the word trim used to describe the inside of the valve, whether it's a vertical rising stem valve or a rotary valve. You will have a inner construction that designates the trim. In addition to that, we will certainly need some sort of an operator. This particular operator we're showing here is a pneumatic diaphragm operator. In other words, it has a pneumatic signal that a controller or an IP transducer or some form that's telling this valve the position that it desired to be. And the air pressure applied in this case of the pneumatic diaphragm is on the flexible diaphragm area, gives the force in this case to make the stem extend or the plug to seat into the seat ring on an increasing air pressure. If you recall before, we talked about pressure is equal to force per unit area, and force is equal to the pressure times the unit area. So whatever the pressure is on the diaphragm surface area will give us our movement of our diaphragm actuator, and it will also move the stem in a downward motion. The spring is compressed as we move this down, and this would give us a fail open air to close valve. In other words, increasing air pressure, in this case pneumatic air pressure, would move the stem down, seating the plug into the seat ring. If you remove all of the air pressure, the valve would then return to a full open position. This gives a fail open air to close operation. These are all some terms that you'll hear. The operator could be a pneumatic diaphragm, a pneumatic piston, electromechanical, electrical hydraulic, many different types of actuators. We're showing a pneumatic diaphragm on our typical valve. So the point we need to take away from this is some of the common terminologies that you deal with when you're talking in terms of a control valve. And again, the selection of a control valve for each application is basically very unique. very individualistic because each valve is selected based on service, the type of material, the corrosivity, the erosivity of the materials. You have to select not only the body materials, but the materials for the trim, and that could be a source of questions that I would encourage you to have a material selection guide with you on the exam. These can be found in many different types of publications. One excellent course publication is the Fisher Control Valve Handbook. I think it's in its, I don't know what edition it's in now. This particular handbook goes back a long way, but in that handbook you'll find much good, useful information dealing with control valves, notably some material compatibility charts that helps you select based on the corrosion characteristics or the erosion characteristics of materials of construction, both for the body and for the trim, the plug and seat ring, or whatever type of trim you have. One other final piece of information on a typical valve is, in this particular case, which is a linear rising stem operation, is packing. These packing, with the packing polymer that compresses some material around the stem to allow the stem its linear motion, but at the same time to seal off from the atmosphere the exposure to any of the materials inside the valve. So you have, this is normally of a Teflon V-ring or some sort of graphite packing. In the olden days, we actually had asbestos packing, but you, of course, won't see that anymore. But you do have, so here we have the valve body. Yes. I'm sorry, did someone say something? Excuse me. Here we have a situation where we are dealing with the terminology of the control valve, which is typical from all different types of valves. So this is very useful no matter what type of valve that you may have. This can give you some of the terminology with the actuator, the valve body, the trim, that kind of the valve packing, and so on and so forth. Now let's look at the valve in a control loop. In a control loop, we see a valve in this particular case controlling the water flow from a water main. The temperature is being measured at this point and is being controlled by a temperature indicating controller, which is given an output, pneumatic output, to the control valve. So as the process gets warmer, you add more valve to the heat exchanger. As the process line cools down, you maybe close off on that inlet valve. So we have a situation here of seeing exactly how the control valve looks in a particular PNID or in a singular loop. And there's many different pieces of information that can be added to the control valve. There's different symbols for control valves, as we looked when we talked about symbology, or you can use the term air to open, air to close, or fail open, fail closed. You can put an arrow on the stem. So there's much information that can be put on the P&I that we talked about some in some of our earlier sessions. So this is what the valve looks like in the control loop. Now, control valve types are different types of how they're built. They come in many different forms and fashions. Well, a major type is a globe valve. A major, one of the most used control valves, along with a ball valve and a butterfly valve, are probably three of our more popular control valves. And these are physically the type of control valve bodies you will run into. You also see a diaphragm or a pinch valve used in many cases. And these have flexible trim liners that are simply compressed across the line and are used for control in some cases, but are also used for on-off as well as control. And we see some plug valves that are used for on-off control primarily, as well as gate valves that may be used for on-off control. And so these are different types of valve bodies, and then special cases you will see valves built with an angle body that are on occasion used as far as the control mechanism is concerned for a particular loop. But these are just some of the many types of control valve that you might run into and that you will need to know a little bit about on the particular exam, because they may ask you for application information. You can also select different types of actuators that I mentioned earlier: spring diaphragm, piston, electrohydraulic, electromechanical, and all the different types of applications and forces will determine what's needed for the application on the particular valve, and that how it would be actuated as far as the operation is concerned. So different types of actuator types, we'll mention some of those as we go along and have a little bit of time. The diaphragm actuator, one of the most popular types of actuators. This is showing a cutaway of the actuator. The stem that's operated, a linear stem, rising stem. This particular one is an air to close, or sometimes called a direct acting air to extend. As you apply a more air pressure above the diaphragm, the direction of movement of the actuator will be in a downward motion, taking the plug into the seat ring, or giving you an air to close, fail open. If you remove all the air pressure, you will get a movement back vertical upward, which would be a fail open air to close valve, sometimes called direct acting or air to extend. So all of these enter into the actual operation of the valve, and again you can see the spring seat, the spring adjuster that you have. So this is a typical air to close, or direct acting, if you will, air to extend actuator. And you can have this type of actuator, or you can have an air to a reverse acting, air to retract, air to open type action. But in both cases you do get a failure situation, so that when you lose power you do go to a failure mode. Electrohydraulic actuators have some advantages and disadvantages that are noted here on this slide. And I would note here that these are used in some cases, and they have some good points, like a good output capability. They're very stiff. They go to a fixed position. They throttle good. They have a very fast stroking speed. However, on the disadvantage side, they're still relatively high cost. They're a little bit more complex, maintenance a little bit more difficulty. They're rather large, and also if you do want the fail-safe action, you will have to add some accessories that make them a little bit more difficult to apply. Electromechanical, along the same line, and this is used many times because it's very handy. Particularly, you don't need air. They're compact. They operate very well. They do cost a little bit more. And again, the fail-safe problem is a little bit emphasized there, because you would probably have to have a battery or something along that line. Also, due to the fact that it is electromechanical, you would really not want to have this in a heavy-duty cycle application, because it would tend to wear out and give you maintenance difficulties. So this is some advantages and disadvantages when using the electromechanical or hydraulic type actuator. Positioners can be added to control valves. They're exactly what they say. They're there to position the valve. If you have a control valve sitting in a line and you put a certain air pressure to it, excuse me, I just went to the wrong slide there. You have the output from the controller coming to the valve, but at the same time, you don't know exactly where that valve is going to go. But a positioner actually is a two-mode controller with mechanical feedback on the valve position, so that if you put 9 pounds to the valve and it's set up for a 3 to 15 pound air to open, it will go half open. Other applications, a couple of them briefly that are shown here. are to split range valves, so that if you need to control both a precise low and high flow rates, you can control like this. For instance, a smaller valve here, maybe air to open 3 to 9 pounds. And when you're needing that low flow and you're throttling in the 4, 5, 6 psig output, you will notice that your large valve, which is in the bypass shown here, would be closed because it doesn't start opening to 9 pounds. As you start calling for an increase in flow rate, and you need a higher flow rate through the line, when the output from the controller reaches 9 psig, this valve is completely wide open, but you're now beginning to open the big valve here because it is in a circumstance of 9 to 15 pounds, and therefore you can control the higher flow rate. Then you look right below this, another situation you run into split ranging valves again can be a situation where you're going to pressure using some inert gas to a process, or you're going to vent the excess pressure off to a flare or some other relief system. In this particular case, what we've done here is set up this the pressure valve, air to open 9 to 15 pounds, and the relief valve set up air to close 3 to 9. So if the controller output is 9 psig, both valves will be closed. Now, as the pressure drops down, in this particular case, we would want to have a reverse acting controller so that we would start increasing the pressure, and as the pressure starts going above 9 psig, the valve from the inert gas would begin to open, putting pressure on the process. Notice that the other valve is air to close at 9 psig. It's already closed, and increasing pressure does not change its situation at all. Now, if the pressure starts building up, we would gradually close the inert valve to the point that we'd go below 9 psig on our output. Then we would have a situation where the vent valve would begin to open and would vent off excess pressure to the relief system. So this, and you can do the same operation by using the output of a distributed controller, distributed control system, to split range and do something along the same line. But you can do that mechanically, if you will, by using valve positioners, which valve positioners are very handy in some cases when you have a large valve, high pressure drops, maybe you have mechanical stickage and this kind of thing. Valve positioners can be very handy, very useful for this type of situation. Okay, let's talk about how our control valves are rated, how they're tested. All manufacturers have some sort of a test loop. This test loop is a closed system with a pump and a closed return. It's very close coupled, and they have the ability to control the upstream P1 and P2 pressures of the control valve, and then the control valve itself can be put in various degrees of open, 10% open, 20% open, or whatever, and then adjustments can be made by the people running the test so that they can check the capacities of each different type, style, and size of control valve. So they run really elaborate tests to get the flow characteristics. Now, when you go basically to the C sub V equation, this is the calculation or the equation relating C sub V, which is the flow coefficient of a valve. The C sub V, we need to recognize that it is the flow coefficient. It's how the valve itself is rated with respect to the operation of the valve. So C sub V is the flow coefficient, and you can see from this particular calculation, which we're not going to derive this as far as the theory is concerned, the flow rate Q may be gallons per minute times the square root of the specific gravity divided by the differential pressure, which is the pressure drop across the valve. Now, this is the basic simplified equation. If you'll recall, when we talked about orifices, plates, and other types of pressure differential devices. The flow was proportional to the square root of the differential. And you'll see here that we have the same situation because a control valve actually is nothing more than a variable orifice. It is a variable restriction in the line, and the same principles of differential pressure and square root relationships still apply to the control valve. So you can see that the flow coefficient you need is directly proportional to the flow rate. It's directly proportional to the specific gravity, inversely proportional to the pressure drop that is available or given to the valve. But this is your generic CSE equation for liquid flow. If we take this a little bit further, though, and we look at how the valve is going to be installed, it will not be installed like it was on the test loop. It will not be installed like it was in the lab. It will have various other characteristics and attributes to take care of. The pump, there's a pump curve, of course, as you back up and down on the pump curve with respect to the discharge pressure and the flow rate. You have elevation changes. You have frictional losses in the line and in elbows. You have frictional losses in different places. And your control valve actually becomes one of your contributors to the overall picture based on the fact that you do have all of these different devices, parts of the line, and fittings that are contributing pressure drop to your nonlinear actual installed system. So you have what's called the inherent flow characteristic of the valve, and then you will have the installed characteristic of the valve. The installed characteristic being driven by and controlled by the fact that you have a non-linear system that you have installed the valve in. And let me explain that briefly. Let's take an elbow. An elbow in the line, like I said, you'll have frictional losses in the line, but you also have losses in fittings. This particular device, it's a fixed opening. We're going to take this and say it has a flow coefficient of 240. We're going to put water through this. And if we decided we wanted to calculate the pressure drop through that elbow, the equation would be Q squared times G divided by C sub V squared. Again, based off the fact that we're coming from the base equation that's shown at this point here. So if you plug these numbers into this particular equation, the differential pressure is equal to 0.0000173 times the flow squared. Remember again that the flow rate is proportional to the square root of the differential pressure. So therefore, if we take this circumstance and say we have to control from 75 to 450 gallons per minute, and we do the calculation of the pressure drop through this elbow, we'll have 1/10 of a pound drop at 75 gallons per minute, but we'll have a 3.5 pound drop with a flow rate of 450 gallons per minute. Now, that means that the valve is the one device in the system that is adjustable, and therefore it receives whatever pressure that's not being used in either elevation changes, fitting losses, or friction losses, or equipment losses, is left for the control valve, and therefore you have to check and make sure will it handle the maximum flow condition and the minimum flow condition, not just one condition that we normally think of. So we're going to talk about that a little bit later as we talk about application and the installation or the installed characteristics. Quickly, you'll hear people ask about or talk about different types of valve characteristics. Is it quick opening? In a quick opening valve, the trim is designed such that you get a rapid increase in flow as the valve first begins to open. Or is it a linear valve where the inside is designed to give a flow rate proportional to the amount of travel, and the change in flow rate is constant with the valve travel? In other words, at 25% open, I get 25% capacity of the valve and 75, and so on and so forth. Or is it an equal percentage trim characteristic which is very, very usable, and the one probably that's about 75 or 80% of the control valves in use now are probably equal percentage characteristic. This one is sort of hard to explain in some cases. The change in flow rate is always proportional to the flow rate just before the change in valve position is made. In other words, at low percent open, low changes in the flow rate as you open the valve, and the more open you become, the flow rate changes more and more because it's based on the rate of change of the position just before you make the change. Or are we looking at some sort of a modified percentage or modified parabolic trim where you get sort of a throttling action at low percent and then almost linear after the first 20% of the opening? Now the question, some people say, well, why do you need all these different types of characteristics? It is because you have all different types of control characteristics that you need based on the type of control system that you might have. If you look at these characteristics plotted, this is the quick opening, the linear, the modified parabolic, and the equal percentage. And again, if you looked at the application of these, you'll find that the equal percentage is the most applied, and also that these are the inherent flow characteristics, but you're installing this valve in a nonlinear system. And when you install it in a nonlinear system and you begin to take into account the system pressure drop, then you have to look at the actual installed flow characteristics. And so depends on what type. As I said, equal percentage is probably 80% of the applications, linear maybe 10, and the quick opening maybe another 10. But notice on the quick opening, you have to be very, very careful in using that, because in the very first early part of the opening, you get a real high flow rate, and that's why that high gain, that's why it's called a quick opening, whereas the others give a little bit more of a change that's characterized as they proceed in their throttling capacity. Equal percentage can be expressed like this. You'll notice in this particular case, as we move from 20 to 30, we get a 50% change in our CSE rating, but that's based off of the 5. If we go from 30 to 40, we get another 50%, but this 50% is based off 7.5. So as we get more open, then we get a higher increase in flow rate. And the equation down there sort of shows how that operates, and its performance of the valve rangeability, which is normally in the 7 to 1 category, and the valve percent open. And as that valve percent open increases, then the C sub V begins to increase faster as a percentage of the maximum C sub V. These are all determined by the physical construction and how the internals of the valve of the trim are built. If you move and look at a linear, you see exactly what we said before. It does increase a fixed percentage, but it's fixed percentage all the way. And so 50% you get half the C sub V, 20% you get a fifth of the C sub V, so on and so forth. So the linear is exactly as it says. The process gain, and that's the reason the valve, you need to have the valve in there operating its normal operating point, because when you change the input to the process system and check the change in the percentage of the measurement, that gives you the gain, and the gain is determined a lot by the valve percentage and the part of the curve that you're operating on. So that's why the tuning, we talked about having the valve in its normal operating position, so that when you made a 10% change in the signal, you could see a process change that would really be representative of that particular process. So you need to always be aware of that. A couple other terms that you run into, rangeability, basically talking about how much you can control to how the minimum you can control. And also we talked some about turn down, which is the maximum flow to the minimum controllable flow, and we'll look at that here in just a moment. Also, that turn down becomes a very important part of the valve consideration. Installed characteristics are affected by the valve style, type, and also what is the percentage of the system pressure drop that you will be able to have across the valve. You need to have a valve in the 20 to 50% of the system pressure drop, because what happens when you actually plot the valve plot out, you see these curves where curve 6 in this particular case would be the actual inherent or laboratory type conditions. But if you change that to 50% of the system drop, notice how the curves begin shifting back to the left, and also though that this equal percentage valve becomes a little bit more linear operation up in the midpoint there where you will want it operating. And valves you do not want to have operating below 10% open because you get down too near the seat shut off. And of course they will control up to 100%, but as these curves shift due to the nonlinearities of the system, they shift back to the left as we see here, then we impact drastically our ability on our controllable flow, and we want to make sure we do have some capabilities in the 10 and 15 and 20 to 1 categories. So the equal percentage trim becomes a very usable trim when you consider the maximum minimum flows that you may have to have as far as your application is concerned. If you look at the linear characteristic, notice here we start with a linear situation, and we get this same movement if we plot the curve on an installed characteristic. The curve again will shift to the left, and notice that this valve, as it moves back to a situation, let's just say, where it only has 10% of the system drop, curve 2 begins to look very much like the quick opening, and your linear operation has become very detrimental. So unless you have a lot of the system pressure drop across your control valve, the linear will shift back into a situation that will probably cause you some problems as far as controllability is concerned, because if you look here at the different situations of pressure drop flows and all, you start out with only a 10 to 1 rangeability, and it goes down very quickly. So the linear valve is good for certain types of level control, perhaps a slow process. In some cases it don't vary a lot, but the linear trim has some limitations that's overcome by the equal percentage. Flashing, a phenomenon that you might see on the exam. Flashing is a situation of where what we're looking at here is a pressure profile across the valve moving from left to right. We're looking at a situation of the pressure through the control valve, and we're looking at the actual pressure that exists in the valve at any one time. And notice we start having our pressure drop just like we did through an orifice plate. In this case, we drop below a certain pressure called the vapor pressure. That is the pressure at a certain temperature. If you drop below that, you start moving from a liquid state to a gas. And you can have a severe control problem there, because you will choke back on the flow rate, because the vapor is formed takes up a larger volume than the liquid did. That's called flashing. A secondary condition that you can run into then from that is called cavitation, which we'll look at. But you move to an outlet stream, part liquid, part vapor. It's hard to avoid this, but you might be able to locate the valve orifice so that it discharges directly into the receiving vessel. But another problem is called cavitation. That's where the pressure recovers in the valve body or downstream there above the vapor pressure, causing an implosion of the valve bubbles. And you can see this time-honored picture here of the damage from the implosions of all of these bubbles. The vapor bubbles that form, then they collapse, makes a lot of noise. It sounds a lot like gravel rolling down the pipeline, but it's eating away and doing damage to the mechanical characteristics of your particular metals in your trim and your valve body. That's cavitation. You might have a question dealing with cavitation. And cavitation, if we look at it, again, looking at the same movement left to right through the valve body, and we're checking the pressure at different points. Again, we drop down and we reach our vena contracta, which is a point of lowest pressure through the valve body, just like it was in an orifice plate. And then we start recovering, and now we recover above the vapor pressure, which was the pressure at a fixed temperature below which the vaporization starts taking place. We recover above that, and that causes the implosion or collapse of those vapor bubbles. It causes danger to your valve, sizing problems, and many, many other things that can happen to you. Many times you can't avoid it, sometimes you can. There are certain valves that are built with what they call anti-cavitation trim. You can select a valve with a higher pressure recovery coefficient, or F sub L. A globe valve, for example, does not have the tendency to flash or cavitate that a ball valve does because it has a higher F sub L value. You can relocate the valve to a point of higher static pressure, which can tend to help out on the reducing the cavitation. You can put an additional restrictor, or you can put another valve downstream to try to break up the pressure drop to the point that you don't have as much cavitation problem. But it is a real problem that has to be dealt with, and you can select a hardened trim, but that does not stop the cavitation. It only prolongs the surface. So that has to be dealt with, and it's a separate tile. You get noise involved with some of these valves. You will not have to do any kind of noise calculation, but I think you need to be aware that noise can be a problem at certain levels. It can cause pain, and there are OSHA requirements with respect to how much noise a person can be subjected to for certain types of working conditions. So our valve body style determines proper application. We have to select those. We'll talk about those a little bit later. The actuator is based on application and utilities available. Each valve style has certain flow characteristics. You've got to deal with pressure and temperature considerations on flashing and cavitation just like you did in a orifice plate or whatever, and different types of capacity ratings for specific sizes or C sub V's or flow coefficients. And control valves many times are the primary final control element, and you will definitely have some problems along this line on the exam. Okay, Summer, let's pause now for just a moment, and let's see if we have any questions. If you do, be sure and let Summer know. And Summer, I'll give it to you right now.
If you'd like to ask a question from the phone line, please press star and the number 1. Again, that's star 1 to ask a question. And there are no questions on the phone line.
All right, thank you very much, and we'll move ahead. Let's talk a little bit about sizing the valves now. We've talked about the valve itself. Let's get into some of the sizing. I don't know how much sizing may be on the exam, but you need to be aware of the equations and how the different physical parameters interrelate with each other, so that if they ask situational questions, you can deal with that. So we're going to look at a little bit of liquid, gas, and steam, and you will not be able to take part in using a computer on the exam, so you will have to use a calculator for any sizing that you were to have to do on the test. All right, first of all, I mentioned C sub V earlier. That's the valve flow coefficient. That is defined as the number of U.S. gallons of water at 60 degrees that will pass through a given restriction. In this case, it's going to be a valve wide open per minute with a pressure drop of 1 psi. So the maximum C sub V of a valve is strictly defined by this equation. It is the flow through the valve in gallons per minute with a 1 pound differential of water, specific gravity 1. And in this case, we are not going to be concerned with the piping reduction factor, F sub P. And you really won't have to take that into account on the exam either. That is a factor that's put in, first of all, rules of thumb on control valves. Typically, the valve will not be line size. Typically, it will be one line size smaller than the pipe it's installed in. If that's the case, and you have a 4-inch valve and a 6-inch line, you would have a 4/6 concentric reducer, which would have a small rating on the factor, rather, in the valve sizing, and that's what the F sub P would be. For our purposes, we will not worry about that. We'll basically take F sub P to be equal to 1. But here you can see actually that how the C sub B comes into account. Then they open the valve at 80 or 60 or 40 or 50%, get the 1 pound drop again, and that gives the C sub B at different points of opening. And that's how you generate the curve that we looked at a little bit earlier for each different type of valve and each different style and size. That's how they plot the curves for this particular size and style of the valve. They're plotted from 0 to 100% with the 1 pound drop of water passing through the valve, and that's actually how they are actually able to relate the valve size. So that's how we get set and look at that circumstance. So that's the definition of a flow coefficient. Critical flow, we mentioned the vapor pressure. When that vapor pressure, when the pressure at the vena contracta is lower than that vapor pressure, the fluid will tend to flash and possibly choke the valve. And actually that can be calculated by checking the maximum delta P, or the delta P allowable, and notice that it's based heavily on a factor called F sub L. And the F sub L is critical, and for instance on a globe valve, it's an average of about 0.85. For a ball valve, that average is about 0.6. Actually, that value is provided by the manufacturer for any particular valve at a desired opening, and that is the factor, the pressure recovery coefficient. You'd like to have that as a high value as you can, but you can check to see if the valve is going to flash, is going to give a problem. It's based on the inlet pressure, also on that vapor pressure, which again is determined by the temperature, and one other factor, which is the critical pressure factor, which is shown here. It can be calculated again based on the vapor pressure and the critical pressure. For instance, on water that's 3,206 psi. That enters into that to a degree also, but primarily the F sub L is what determines how well that valve is going to function in a severe pressure drop situation. So all we're talking about there is we're seeing that there is a point to where any additional pressure drop, you're choking the valve and you're not able to move any more liquid through that valve. The gas volumetric flow rate is shown by this particular equation here, and we'll use a variation of this to calculate a C sub V. This is one form of that particular equation, and again we're dealing now with volumetric flow rate, in this case standard cubic feet per hour. We're talking about a compressible gas. The compressibility factor we normally will just use as a factor of 1. We do calculate a valve pressure drop ratio, which is the differential pressure divided by P1, and there is a limit of that of the critical flow that will limit any, we get the sonic velocity that will limit any increase in flow. One thing to notice here too, this temperature is in degrees R, degrees Rankine. If you'll recall, we talked about that earlier. Also notice the impact here. You can see how the F sub L plays into the equation for the limit of the pressure drop ratio. The higher your F sub L, of course, the better your situation will be. For instance, 0.85 will give you a better X and T than a 0.6 squared that will give you there. So the selection of the valve style is very important. I don't know that you'll get that deep into the sizing because you simply do not have all the information, but you do need to understand the principle here that this slide shows primarily, that there is a limiting factor on X, which is the dP divided by P1, and as you go above that particular limiting factor, you will not get a further increase in flow rate. So you do need to be aware of that and actually what the definition of the pressure drop ratio factor is. And typically you can use that to calculate and see if you do have a fully choked flow condition. So again, that's for compressibles or gas or vapor type application. When you get into steam, of course steam also is a compressible, but we can take the equation and they go through some different manipulations and some different assumptions, and the simplified equation we show here can be used, but we're going to go to a little bit more, a little bit better application of that, and this will be our steam, I call it the plant equation that we show right here. And again, this one is pretty straightforward and derived from the gas equation, except our W in this case is in pounds per hour. I think we've already talked about the definition of X, but X is our pressure drop ratio. Then we have another calculation. We talked about our X and T, which is 0.85 times F sub L squared. Then we introduce a factor here of Y, which is 1 minus X over 3X of T, and that's an expansion characteristic that we calculate based on the differential and the inlet pressure. Then we plug YX into our equation and also our P1, which is our upstream pressure in PSI-A, and then we bring one additional note in here that we call the specific weight, pounds per cubic foot of the steam. Now be careful that you use pounds per cubic foot, not cubic foot per pound. You can find this in various steam tables, just like you can find different saturation temperatures and pressures, but this would be specific weight, or if you want to call it density, pounds per cubic foot of the steam, and you can use this equation as the general steam valve sizing equation that's been derived, and you can find all these other characteristics that you might need to as far as the sizing a steam control valve. So there's one other thing I'd like to point out. It really comes in handy, and it's amazing that this actually works out. If the pressure drop ratio, which is the ratio of the differential pressure to the upstream pressure, is equal to or less than 0.1, we can use a highly simplified calculation of the flow coefficient that says if you take the flow rate in pounds per hour, mass flow rate, pounds per hour of the steam, divide that by 2.1 times the square root of the differential pressure times the sum of the pressure, it is amazing the accuracy that you can get. Only though when you have the situation that we display here. This would mean if you have a relatively low pressure drop compared to your upstream pressure, that you can just take the pounds per hour of steam divided by knowing only the pressure P1 and P2, taking the differential and add them together, and you can actually calculate the C sub B required for that particular valve. That's a handy equation. It's neat to use at least to check out an answer. Now, this is the summation of the equations. These will be in your summary of equation booklets that I have sent to you by email, those of you that requested. But you can, and these are found in a section in that booklet. This has the standard liquid equation, the gas and vapor by volume, the gas and vapor by weight, and then the correction for the superheated steam, which is a very simple correction. You calculate the C sub V for saturated, and then you're able to take this simple 1 plus 0.0007 and times the degrees of superheat, degrees F of superheat, and that will correct your C sub V for the superheated steam. So this gives you the basic simplified direct equations. All of these are characteristics of terms that we have talked about and used as we went through today. I would point out again, the temperature here is in degrees Rankine, that pressures are in PSIA, and the fact that in calculating some of these factors, you do need to determine, am I using a globe valve or a ball valve, and then that gives you the difference in some of the other characteristics that you're going to be plugging in to size that. Okay, so that's a little bit on valve sizing there. Again, you got to know valve flow rates, you got to know the maximum, you got to know the minimum, you have to know pressure drops in those circumstances, so it's a little bit more complicated than it may appear. Which valve do I need? Well, you want it to perform well, you want it to be installed and be maintainable over a long-term situation. That's some of the scenario questions that you might have, and I think we do need to remember that control valves are rated by flow coefficients. The flow capacitor valve is based on that flow coefficient, the pressure drop across the valve, the fluid temperature, and the fluid properties. You have to size each application looking at situations that might give you flashing or cavitation situations. Globe valves have a higher F sub L value, which is the pressure drop recovery factor. It does not flash as easily as does ball valves. Ball valves, of course, will be good application for sludges or slurries or things of that nature. The globe valves are good for clean liquids, gases, and steam. So there's a multitude and a myriad of situations that you need to be aware of and be prepared to address as far as how do you install the valve applications, and certain situations that you have to be aware of. So we'll pause now for just a few seconds again and let Summer check with you to see if anyone has any questions. So Summer, I'll turn it back to you.
Again, if you'd like to ask a question from the phone line, please press star, then the number 1 on your telephone keypad. We have a question from Charles Nielsen of Progress Energy.
All right, go ahead, Charles.
Yeah, I just wanted to confirm, you had talked about the temperatures being in degrees Rankine. I just wanted to verify, because the valve sizing for steam talks about the superheat being degrees Fahrenheit above the number of degrees superheat as being degrees Fahrenheit.
Yes, it was still that particular correction, and I was moving back to there. That particular correction is in degrees F. You will have the degrees Rankine will be used in the equation, and you would get a C sub V value for that. But then you would need to correct based on the degrees Fahrenheit above the saturation temperature. That's correct. Thank you.
Great. Just wanted to verify that. Thank you very much.
Again, if you'd like to ask a question from the phone line, please press star, then the number 1. And there are no further questions.
All right. Thank you, Summer. Thank you very much. I appreciate it, and we'll move ahead. And I think I will pause here for just a second and do something I didn't do last time. I'll give you my email address, gwillbank@al.com, in case you don't have that. I know a lot of you do, because you have been corresponding with me by email, and that's fine. Last time, I forgot or did not offer you example set of questions number 3 of test example items, and this time I'm offering the set number 4. So if you'll send me an email, and actually what you should have at the conclusion of today's seminar, you should have a summary of equations, a bibliography of references, and then you should have sample problem set number 1, 2, 3, and 4. So if you're missing any of those, if you'll send me an email and tell me which ones you're missing, I'll be glad to send those to you in my return email. Again, my email address is shown there, gwillbank@aol.com. Or if there's any questions, some of you have sent me questions about certain problems or something that did not look right, and there are mistakes made by everybody that does any of this type of thing, and there can be, and I'll be glad to try to clarify any of the problems or questions that you might have. But again, you should have the summary of equations, a bibliography listing, and then 4 sets, 1, 2, 3, and 4 of sample problems. And so if you're missing any of those, send me an email, and I'll be glad to get those back in order for you. Okay, one of the items that sort of surprised a lot of people maybe several years ago, but pressure relief devices or relief valves or safety relief valves are included on the exam. In fact, they are listed as almost 4%. You'll probably have 2 or 3 problems on relief valves to go with the probably 6 or 7 control valve problems. So we do put a little bit in here. I'm looking at the specification right now for the control systems PE exam, and they do have valves, pressure relieving devices, motor controls, and other final control elements, even like solenoid valves and things, self-regulating devices. And we're trying to catch as much of this as we can on 1.5 hour segment. But as you all are well aware, there's entire books written about control valves, relief valves, and there's classes that's taught. I think ISA even has a 3 or 4 day class just on control valves. And so we're trying to catch as much as we can, but you'll need to take the information that we have today, take some of the reference books that we've been referring you to, and then do some additional study on your own. So let's look at relief valves, a little bit about terminology, how you use them, a little bit about sizing relief valves. First of all, what is a relief valve? Well, generically, a relief valve relieves upstream pressure in proportion to whatever that pressure is. If it goes above a certain pressure, it relieves that. But does it, a safety valve relieves it sort of in pop action or rapid full opening. A safety relief valve might be either of the above to protect personnel. In other words, one terminology for a pressure reducing valve, it can be a self-contained modulating pressure reducing valve, or is it a safety valve that has pop action, or if you actually have personnel and equipment endangered, that becomes a safety relief valve. So it's all sort of some of the same terminology. It depends on exactly how you look at it, how you count your words of that. Let's look at some relief valve terminology, and we'll get into an actual example here in a minute. Operating pressure, that's the normal vessel or the system working pressure. And the maximum allowable working pressure, that means if you have a system designed and set up, it could go up to this as a maximum working pressure. That's not a burst pressure, but that's a maximum allowable working pressure. Now the set pressure is going to be the inlet pressure to which our safety valve is set to operate. That's the base pressure that we say that's the point where we got to start protecting or relieving or doing something. But it has some other terminologies involved there also, like what is the rated capacity? That is the flow that has to be carried by this relief device at some given percent overpressure permitted by code. Now this code we're referring to here is the ASME, Unfired Pressure Vessel Code. I think it's section 8 or something like that. you probably need to look at the SME Unfired Pressure Vessel Code to see about this overpressure. That means that at a certain overpressure, and typically I think it's for a one relief valve device, a one relief valve setup, that is 10%. Now that means if I've got a valve that's set at a nominal pressure of 100 psi-G and 110 psi-G, I must be carrying whatever that stated capacity that I've needed for my system. That flow must be being carried by the device. I guess you could say it gets a little complicated, and we'll go back through this in just a moment, help you some, I believe. Also, I'd like to note at this point, too, though, that the operating pressure and the set pressure, you need to be aware that you need to have a differential between those two. If it's not at least 10% or 25 psi minimum, you'll have the set pressure and the operating pressure so close to each other that the valve may tend to chatter. It may tend to what we call percolate, or sit there and bounce back and forth. It's running along and it's too near the pressure, so it tries to open up a little bit. So whatever your operating pressure is, there should be a gap or a differential between that pressure and your set pressure in order to allow the system to operate and yet maintain control at the same time. So this is very, very critical on this part here as far as this terminology, and we'll try to clarify that some in just a moment. All right, what's some of the different parts or things that you may see called out on a relief valve? Well, first of all, of course, you're going to have a body of the relief valve, and that body is going to have an inlet and an outlet. The inlet's going to be attached to the system or to the pipe that you're relieving from, and of course over here on the outlet, this relief is going to be going out to some relief system or relief header. The inlet at this point here will be the same size as the nozzle. It shouldn't be any smaller than the nozzle size on the particular vessel or the system. You will also see that the inlet and outlet will not be the same size due to how they're constructed and how they're set up. For instance, when you read about a relief valve, you may read that the relief valve is a 4x6, or you may see a relief valve that says it's 7x8, 6x8. What this means, you have a 4-inch inlet and a 6-inch outlet, or you have a 6-inch inlet with an 8-inch outlet, as the case may be. But those sizes are going to be dependent upon what's needed for the valve based on the sizing and the square inch calculation for the disc, the surface, the area of the orifice within the valve. This calculation will be done in a situation that depends on the flow rate that needs to be carried through the valve. We have a certain size, certain square inch orifice size that will be calculated. Depending on the size of that orifice, we will sometimes it might go in a 4x6, and other times it might also be the size that we need, a 6x8. So the valve size is determined by the calculation of the square inch disc opening that we must have there. So we have a disc and a body, and we'll have different materials for those. We have a spring, much like on a control valve, except in this case we have a adjusting screw here. Instead of a pneumatic pressure mashing it up and down in a throttling fashion, we have an adjusting screw set with a certain fixed pressure that this valve sets in this position until we reach that pressure, and then it pops open and relieves the rated amount of capacity that's needed. There'll be a cap up here. This all is called the bonnet. The top works of the valve, the relief valve, this is called the bonnet. We did the same thing on the control valve. Looks very similar. The relief valve body is basically like an angle control valve. again, you have a variable orifice situation, a pressure reducing situation. The flow rate depends on the pressure differential across the relief valve. And you know, you can go to Ferris, Consolidated, Anderson Greenwood, Crosby, manufacturers' information and find these cutaways. You can find the materials of construction that are available. You can find sizing information, etc., etc. And they're all pretty much, basically pretty much standard for the most part, because they're governed by different characteristics out of ASME and the vessel code. All right, for steam sizing, which I think would be the most appropriate, this is the equation that you'll find in the information from these different manufacturers. Again, A sub C we're looking at here is actually the square inch valve nozzle calculation, and we want to find out how many square inches do we need to relieve a certain capacity at a certain set pressure from this operating system. Our W is going to be in pounds per hour. P1, that's the rated flowing pressure now at PSIE. Now that's not the set pressure. That's not the set pressure. We're going to look at that. The rated flowing pressure would be the set pressure with a 10% accumulation converted to PSIE. We'll look at that here shortly. If you have superheated steam, you might have to have a little correction in that. The Napier factor is only applicable if you have an extreme circumstance of pressure above 1580 degrees. I seriously doubt that you're going to have that situation. The back pressure factor normally is 1, and the coefficient of orifice discharge, K sub D, is a very interesting little factor here. That's actually provided or given by ASME. It is a safety factor, if you will, taking into account the fact that some of the valve manufacturers may cut their sizing a little close. So the government does call for that a little safety factor in there. It's normally 0.855, and we'll look at that in just a moment in a sizing example. Okay, let's look at one. We have 150 PSIG steam header. Normally the valve is going to be operated at 50,000 pounds per hour, but this particular valve, wide open, can flow out 100,000 pounds per hour. Now this steam is going into a vessel or a system that if this valve was to fail, it could overpressure the vessel in some cases, or at least we don't want that to happen, and we may need to relieve that pressure. The maximum allowed working pressure we're given for this particular situation is 180 PSIG, and we're going to set this up with a set pressure of 165 PSIG because we're operating at 150, so that's a 10%. That's fairly close. We should operate okay. In this case, we're given a steam temperature of 440 degrees F, and at that pressure, 150 pounds, that is superheated steam. Now, in this particular case, we're going to calculate our fluid pressure, and as you can see, we're going to take 1.1 times the set pressure, and then convert that over to the PSIA. So 1.1 times 165 and 14.7, and we get a P1, and that, I repeat, is the flowing pressure of 196 PSIA. This is a K sub D, 0.855. Napier factor doesn't enter into it at all. Back pressure doesn't enter into it at all. In this particular case, they gave us a correction factor of 0.98 for the superheated steam. So this is where we get all of our information, all of our points from. They're coming. This information is coming from codes. It's coming from manufacturers' data. It's coming from government regulations, and we get all this and put it together. And again, most of the problem in sizing a relief valve or a safety relief valve is not the mathematics. It's pretty straightforward math. And by the way, this is in your summary of equation booklet also. So let's plug all of these numbers into our particular situation, 100,000 pounds per hour. There's our constant, there's 0.855, there's our fluid pressure, there's our correction. And if you do this, according to my calculator, I got about 11.82 square inches. Now, ASME's defined orifice sizes that are available from all manufacturers, D through T. I'd like to point out, too, that API also has a defined set of situations that says the orifice sizes that are available in certain sizes of valves. So you have to deal with which standard are you working with, which standard is the valve, relief valve manufacturer dealing with. In this particular case of ASME, which we're using here, we found out that an orifice Q has an area of 12.85 square inches, and that's really about 1 square inch above our requirement of 11.82, and that goes into a 6x8 valve. And then, of course, as far as our ratings on our flanges, that should match the piping. Material should match the piping specs. So in this case, you need a 6x8 inch valve, perhaps in a carbon steel, with 150-pound range face flanges, 6-inch inlet, 8-inch outlet, 12.85 square inches orifice Q. Then there'd be some other things you'd have to define too. That would be for a set pressure of 165 and a flowing pressure of 196 psi. So that's some of the terminology and an example of how one would be used. And, you know, a lot of people found this thing sort of interesting because they didn't work with that as far as where they work. They didn't deal with relief valves, but it has been determined that it would be used on the test because enough people say that they do this in their job. Some installation hints: close coupling to the pipe or vessel you're dealing with. Use the same size inlet pipe as the valve inlet. Same size outlet pipe or larger when needed. Now, this little note here is real interesting. Let me clarify this. No isolation valves on the inlet or outlet unless you have particular operating circumstances and processes that will allow that. Your particular location, you may be able to put a shutoff valve underneath that. If you arrange for a car tag situation or some sort of chain situation where you have to go through a process to close that shutoff valve off. Otherwise, you don't have an isolation valve on it without some sort of protecting system, okay? Also, you need to look out for reaction forces and thermal stresses. Vent pipe should have a rain hood and drain, and you need, of course, the noise level need to be checked by the manufacturer. So that's some situation that should not occur on the exam, but I think we need to know about it anyway, so it's just a part of that. So another thing that we might want to make note of here, relief valves are part of the overall safety system, and our final seminar, by the way, will deal with safety instrumented systems. But right now, looking at this as part of the overall safety system, you might, for instance, need to put a rupture disc underneath a relief valve that's dealing with a corrosive gas, and that way you can use a more conventional material for your more expensive relief valve while obtaining a very economical price on a rather elaborate rupture disc. Also, don't put the shutoff valves underneath it, though, unless you do have a protection process or setup that takes care of that. Because what we're trying to do with any of these situations, of course, here, the safety relief valves are installed to protect equipment from overpressure and the resulting damage, loss of life, environmental impact, anything like that. That's what a safety relief valve is. For something bad can happen, and this is one of your lines of defense as far as your safety system is concerned. All right, Summer, I'll pause again now. I'll turn it back to you to see if there are any questions or clarification needed.
Again, to ask a question, please press star 1. There are no questions.
All right, thank you very much, Summer, and we will proceed. We want to look at some sample problems here in just a moment, but right now I need you to do me a little favor. If you would, how many people are at your site for this particular web seminar? If you would fill that out or locate that on this poll slide, we would appreciate it, and when we get this done, we'll look at some sample problems and move to the conclusion of our seminar today. All right, looks like everybody's getting that filled out. Pretty okay. We've got that now. Thank you very much. I appreciate that. And let's look at some sample problems, which are always something that's pretty interesting to see what could be on an exam. This first problem says we have a control valve is to be sized for the following conditions: liquid flow 50 gallons per minute, specific gravity of 0.81, inlet pressure 240 pounds, and a pressure drop of 10. The required flow coefficient for the valve will most nearly equal 10.4, 14.2, 22.2, or 35.5. Well, if we go with our trying to eliminate obvious answers, we can't do that because this actually is a calculation problem. And I think the easiest thing for me to do is just refer us back to a prior slide, and we can look at that. If we go back to the general sizing slide, a C sub B is equal to Q, and we're going to ignore the F sub P at this time, times the square root of G over delta P. This is a situation where our standard sizing, you plug in 0.81 for the gravity, the differential pressure we were told is 10, and the flow rate is 50. We're not given any information about a vapor pressure, valve type or style or anything else. All we can basically do here is plug into the standard equation, and if you do plug all of those information in, I got an answer, and you might check this to make sure mine is right, but I've got, my calculator said 14.23, and of course that would indicate then that we would have a selected answer of B would be the correct answer for this particular question. And again, all we can do there is use our standard equation since we don't have any other information to deal with. All right, the next question, of control valves to be sized for following. This is saturated steam at a maximum flow rate of 30,000, upstream pressure of 40 psi. P2 will be 30 psi according to the flow sheet physical piping arrangement. The required flow coefficient for the valve will most nearly be 260, 540, 760, and 198. Again, I don't see any way we can eliminate anything. We basically do have a situation of saturated steam, 30,000 pounds per hour. In order to save a little bit of time and the fact that I'm not that good with pencils on screen anyway, if we go back to slide 46, we find a steam size equation W over 63.3Y square root of XP1SW. In this particular case, we can calculate some of these numbers. Our X is going to be equal to the delta P, which is 10, divided by the inlet pressure, which is 40 psi. So we will get an X value of 0.25 if you calculate that out. So that's that value for that. The Y, X and T, if we do go over here and select a globe valve with an F sub L of 0.85, we will get an X sub T calculated X sub T of 0.62 because we're calculating 0.85 times 0.85 squared. Then if we plug those two quantities, X and X sub T, into our Y equation, we will get a Y of 0.87. Then we are able to come up to the equation above and plug in our 30,000, our 40, our x of 0.25 and our y of 0.87, and that only leaves us one other quantity. It's called S and W, that being the specific weighted pounds per cubic foot. If you go and look in steam tables, or if you look in other books, you'll find that S and W for this particular situation, or at least what I looked it up to be, was a value of 0.095. 0.095. And again, that's pounds per cubic foot. Sometimes you'll find specific volume, cubic feet per pound, you just invert that, but in this case, 0.095. And then if you plug all of that into the equations and you solve that out, you actually come up with a value of a C sub V of 560. That is a C sub V value of 560. So that would tend to give us our answer, but I want to point out one more thing that you might keep in mind too. This simplified equation, which has only got the flow rate and the pressures involved, notice that our value for this right here was 0.25. It's a little bit more than 0.1, but I plugged that in just to find out how that would work, and the answer I got for this C sub V is 540, which I think tends to tell me that the two equations did agree pretty close to each other, even though the assumption was made outside the bounds that we have. But in any event, if I go back and look at my choices, I do have one choice that fits this pretty good, and that's 540. So whether it's 540 or 560, the point is I got my answer in this particular question. Then the next one is a relief valve problem, meaning for a supply steam header in a plant, determine maximum relief is 100,000 pounds per hour, set pressure 165, maximum allowed working pressure 180. The steam temperature is 440 degrees. Given a assuming correction factor of 0.98 to calculate oversteer for the relief valve is most nearly equal to. I refer you back to where this is nothing but the sample problem that I had inside the contents of our video today. The answer is 11.8 square inches. This just shows you how that problem can be worded on the test and ask the same thing. This goes back to this sizing example of how you work this out and how you get the final answer to it. So I'll just refer you back to that as far as the answer is 11.8. And then finally we have one more sample problem today. In a gas flow control loop, a control valve has the process conditions of 65 and 15, 140 degrees F, gas for electrical weights 40. Then they lay out a purely theoretical situation that if only the open area of the valve X increased, how would the mass flow change? In other words, everything else remains constant. Temperatures, everything else remains. All you do is change the area, and you're looking at mass flow. And we got four answers here. And this is purely theoretical. It couldn't exactly happen this way, but that's beside the point. We do know that our mass flow would be equal to our density of our material times the area. We were given the area as X times the velocity. In other words, instead of rho AV, we got F is equal to rho XB. And for the two different situations, F1 is equal to density 1 times X1 times V1, and F2, the second condition, when we have a different area, is equal to density 2 times X2 times V2. If you divide these out, in other words, if you take F2 and you divide that by F1, and then you cancel out all the equation, the parts that you are the same, you will actually get an answer that says that F2, it's a linear situation, is going to be equal to the F1, which was your original, and then that's just going to be times a value which is X2, which is the original, the secondary area for the orifice exposed divided by X1. And if you look, you will see very quickly that that answer does come and is given by answer C. Answer C would be the correct answer. So if you did work that out, you can play with that some. It's in some of the solved problems that you'll be receiving on your request basis. So that's our sample exam questions for today, and I hope that's been of some benefit to you. And again, send me a note and ask for the sample set number 4. ISA has a complete course on sizing, selecting, and applying process control valves, and a lot of other information, of course, available from ISA. Some of this I've referred you to before. Again, I would like to say there's some places that you can pick up additional information about control valves and items that you might have on the exam. If you're not an ISA member, I would encourage you to join up. It's a great value with a lot of benefits, and certainly some of the things that we do other than supporting the control systems PE license is also providing back for the information and the substance for the certified automation professional and a certified control systems technician. So thank you very much for taking part in our web seminar today, and Summer, I'll turn it back to you to wrap up today's session.
This concludes today's ISA web seminar. Please do not forget to fill out the evaluation survey found in your email inbox. Thank you for attending and have a nice day.